I don't have the phone number. I will send a mail to Avinash ji. Okay. Saturday.
Okay.
I will
Okay.
send. Let us see.
Okay, Professor.
Yeah, I will send him a mail. Yeah.
Recording I started and also live started.
Okay.
Okay. Vijay Kumar sir.
Okay, sir. I'll start. Good afternoon to you all. I welcome you all for this session. I welcome our chairperson, Professor M.S. Sriram, Professor K.V. Sharma, Research Foundation, Chennai, and invited speakers, Professor Avinash Sataya, Professor Amartya Datta, Professor C.S. Aravinda, and Professor Venkateshwara Pai. I hand over the session to chairperson, Professor M.S. Sriram, sir. Thank you.
Okay, just 1 minute. Let me say, yeah. Just 1 minute. I'll send the mail to him. Yes, send the mail to Professor Sate. Let us see. Okay, shall I start the session, please?
Yes, Professor.
Yes, oh good. So the first talk will be by Professor Amartya Datta. Amartya Datta Kumar Datta, he did his PhD in mathematics at TAFR, Mumbai in 1994. Currently, he is a professor of mathematics in the Indian Statistical Institute, Kolkata. He has several research publications in commutative algebra and affine algebraic geometry. For the past 2 decades, Professor Datta has been regularly delivering and writing articles on topics in history of science, especially ancient Indian mathematics. He is a recipient of the Satish Bhatnagar Award in History of Mathematics from the Indian Mathematical Society. The same, in fact, he was the first recipient, and he is also a recipient of the INSA, Indian National Science Academy Teachers Award of that academy. Okay, now over to Professor Datta, Amartya Datta. Please start, sir.
Vijay Kumar sir.
Yes, sir.
Professor Amartya will be sharing the screen, sir.
Yes, sir.
He is a co-host. Just now, I think he joined with another.
Professor Amartya sir.
He said.
Yes, sir. Yes, sir. Fine.
His mic has to be on actually. It's not audible.
Professor Amartya sir, we are not able to hear anything. Please unmute yourself.
Maybe internet problem is there, I think so.
Yes, sir. Yes, sir. Maybe. But Professor is sharing screen and showing something. Why
Yeah,
is not
yes, yes.
visible?
Only showing screen.
Yes, yes. Sir.
Screen, PPT, but
In chat section, anything he has given, you check, sir.
Yes, sir. Yes, sir.
Might be communicating through chat.
No, sir. I didn't get any message up to now.
Sir, Rushkumar sir is not available.
No, Rusi Kumar sir is not there. Because the last session is going on. He is in the another session.
Yes, sir.
I see.
Handling another system.
Okay.
Are you starting? Because there's a connectivity problem for me. Now it is okay. Yeah.
Sir,
Is Prasad Datta presenting?
He has shared the screen, but audio is not working, I think, from his side.
Oh.
We are not able to hear.
I see. Okay.
If you have phone number, then we can ask him to.
Yeah, okay. I have the phone number. He might have muted, you know.
No, sir, not muted. Video also not muted, but we are not able to get anything, any sound or any other things.
See, he said he had some connectivity problem. That's the problem.
Yeah, maybe like that, Professor. Yes.
Yeah.
Can you hear me?
Hello.
Hello, can you hear me?
Yes, Professor.
Yeah, I'm Amartya. Can you hear me now?
Yes, Professor. You are able to hear. Yeah, we are hearing you.
Okay, actually now I've connected through another mobile.
Tell Amartya. Okay. We can see your screen also. Please go ahead, Amartya.
Yeah,
Amartya,
I'm now trying to get into the screen. Yes.
Okay.
Trying to access the screen now.
Okay.
Where is this?
Yes, sir. Yes, sir. Video has come.
Yeah, I'm now this. Where is this? See, this is looking different. Can you guide me? What is the share screen? It was not showing it.
Sir, it was showing screen now. That has been stopped, I think.
Now, can you see the screen?
Amartya? No, I can't. We can't see your screen. 1 minute. Yeah, maybe you are trying. Yeah.
Now it is coming.
Yes, started screen sharing. We will tell you. No, this is a problem for him, Amartya. Yeah, please. No.
Hello, can you see the screen? Hello, can you see the screen?
It
Okay, so can you see the screen?
Not yet,
I think
sir.
we can't.
Not yet. The screen is showing that Amartya Kumar Datta. Now we can see,
yeah.
sir. Now we can see. Yeah.
Okay, so as you know, ancient Indians recognized zero as a number in its own right, not just not a mere placeholder for a place value system. This is a unique contribution to India. Zero as a number, and describe rules of operations with numbers, positive, negative, and zero, treating all on the same footing. So in the language of modern algebra, the Indians had revealed the ring theoretic aspect of integers with zero as the additive identity, and the oldest reference for that is Brahmagupta Siddhanta of Brahmagupta, chapter 18. And there, in that, at the very beginning, it's listed what are the topics under algebra, and the term used there, one of the terms used is kha, rina, dhana, that is zero, negative, and positive. That is one of the things which defines algebra. And Brahmagupta, in that treatise, has given operations with zero, summarized all the operations, all the familiar operations, so I'm not reading them. And interestingly, there is one phrase, zero divided by zero is zero. And this is the statement which is criticized. For instance, David Mumford, in a paper on negative numbers in India, in history of negative numbers, he quotes this phrase of quotes those verses of Brahmagupta on 0, negative, and positive numbers, and then he praises it highly, but with that reservation. The only oddity seems to be his confident assertion that 0 by 0 equal to 0. The rest is as clear and modern as one could wish. But he calls it an oddity. He stops short of calling it an error, which is usually done, that this is regarded as an error. So since the time is short, I'll do one thing. I'll just skip the Sanskrit and come, you can read it on your own, and I'll just straight away read the maths. So Brahmagupta says in words 0 divided by 0 is 0, and this statement is repeated in an ancient commentary on Sridharacharya's Patiganita, and it is repeated by Sripati. Bhaskaracharya is silent about this 0 divided by 0. Brahmagupta goes on to say a negative or a positive number when divided by 0 has that for the denominator. That is, he looks at the fraction a by 0 and leaves it as it is. In other words, he's introducing the numbers a by 0, but in the treatise, he doesn't quite say what to do with them. That is, does not subject them to arithmetical operations, unlike the usual number 0 or negative number. So he doesn't say what is a by 0 plus b by 0 or what is a by 0 plus usual b. And similar statements are there in Sripati. This fraction is called Khacheda by Brahmagupta and Khahara. Both mean 0 divided by Sripati and Bhaskaracharya. And as I told you, that this is something for which historians of mathematics and even mathematicians criticize ancient Indians, and that is the reason for this talk. So, shocking example from Bhaskaracharya's Bijaganita. So I'll straight away come to the problem that what is the natural number which when 0 divided, augmented means that you add, augmented or reduced by this big number, then squared and then augmented by its own square root, 0 multiplied becomes 90. So now write it in symbols, which is what is done by modern historians, that since this number is big, just let us call it C. So what is the natural number? So let us call it x, which when 0 divided, so x by 0 plus C whole square. So C, we can take it positive or negative, and then squared it, and then augmented it by its own square root. That means x by 0 plus 0, then 0 multiplied becomes 90. So this is the problem stated by Bhaskaracharya, and modern authors interpret this problem as follows, that this division by 0, they interpret it as x into t, where t goes to infinity. So they interpret this thing as xt plus c whole square plus xt plus c by t, and calls the and says that you see that this limit. So they're thinking that this is, you have to take the limit of that, and this left hand side is infinite and right hand side is 90. So this is some absurd nonsense given by Bhaskaracharya. This is how modern historians interpret it, as a bad blemish. Now the point is that you have to remember that who are the mathematicians we are talking about. That in the subsequent treatise we will hear from Professor Aravinda, profound work done by Brahmagupta in giving a composition law, which is 1200 years ahead of the time. Bhaskaracharya, he was solving problems of this level, and they are precisely the culprits for doing this kind of thing. So the question which should be asked is that, is the above approach, because it is modern authors who are interpreting their verses in the framework of calculus, but is it the only approach? Is it the only possible mathematical framework to explain the words? So here I should make a digression before coming back to ancient Indian mathematics, that one thing we have to be clear, that mathematics is not merely calculus. Unfortunately, after school maths, high school mathematics, the higher mathematics is usually identified with calculus, and everything which has some kind of sophistication is seen in that light. So that is not the case. So I'll give some examples that something which may not be valid in the framework basic calculus may be valid in a framework of sophisticated algebra. So what I'm trying to do is that a same notation can have a different way of looking. So let me just write down this. That I'll tell you that somebody has written this. 1 plus 2 plus 2 square plus ... equal to -1. Now, should this be laughed at? Very basic question. In the light of calculus, this is something absurd. You cannot do such sum. I mean, for doing infinite sum, mod x should be less than 1. But this is a very valid expression in what is called the two-adic completion of the ring of integers. So it is a bigger ring which contains the ring of integers. And there this is valid. This is modern algebra. I'll give another expression. 1 plus x square plus x to the power n plus ... equal to 1 by 1 minus x. Is this valid? Most people will say that it is conditional only if -1 less than x less than 1. In algebra, x has a different meaning from the meaning in calculus. And this, in that meaning, this is a valid identity. In fact, this condition doesn't make sense there. It is a valid identity in the ring of formal power series with indeterminate x. And there is a conceptual difference between the variable x in analysis, which takes different values in a domain, and the indeterminate x in algebra, which is a definite element of a power series ring. And this is a valid expression. So we have to see it in that light, that modern algebraists are talking about this, and if somebody who is not familiar with modern algebra takes a peep at the notebooks of top algebraists, he will think that some nonsense is going on. And that is precisely what is happening with ancient Indian algebra. So again, I quote a statement from Professor Abhyankar. So in a historical article on algebraic geometry, he is reminiscing. Generally speaking, from Newton to Cauchy, mathematicians used power series without regard to convergence. So mind you, big people, Newton and Cauchy, used power series without regard to convergence. They were criticized for this, and the matter was rectified by the analysts Cauchy and Abel, who developed a rigorous theory of convergence. But after another 100 years or so, we were taught, say by Hensel, Krull and Chevalier, that it really didn't matter. We may disregard convergence after all. So the algebraist was freed from the shackles of analysis, or rather, as in Vedanta philosophy, he was told that he always was free, but had only forgotten it temporarily. Now, these are things you keep it in mind. So when we are looking at the question that did the ancient Indians commit an error? So here we should remember that in modern mathematics, division by 0 is declared undefined. So this is a convention that we have adopted. It's a safe and convenient convention, but still a convention. Now, why this convention? Because there are some difficulties. If you introduce numbers with 0 in the denominator. But this notion that 0 is undefined has led to a deep-rooted belief not only among the mathematicians, but even among the general public, I would say, that division by zero or fraction with zero denominator is impossible. And this impossibility of division by zero has taken such a strong cultural root that even in jokes about film stars like Rajinikanth, with Rajinikanth you have so many impossible statements attributed to him in the internet jokes, that Rajinikanth can answer a missed call. And there are two mathematical statements with Rajinikanth, that he can count 1, 2, he has counted 1, 2, 3 up to infinity twice. Along with that, Rajinikanth can divide by zero. That means something very absurd. Now, the impossibility of division by zero is established often through the following argument, that suppose x not equal to 0 and x divided by 0 is y, then cross multiplication gives you x equal to 0 into y equal to 0, which is a contradiction. And the proof by contradiction shows that you cannot have this. And many putative scholars they will tell you that because Indians did not have proof by contradiction, therefore they did not realize that you cannot do division by zero. Now here comes the questions. Can one not have a valid system with numbers y equal to x by 0 introduced by Brahmagupta with suitable restrictions on the operation of cross multiplication? So you permit x by 0, but don't permit this, if x by 0 is y, then x equal to 0 into y. No, don't permit this implication. What's wrong with that? And you take an analogy. Look at the rule. Root a into root b is root ab. So with positive numbers, this rule has been applied over ages. And this rule was a bar to introduction of complex numbers. You know that root over minus 1 is called an imaginary number. That is, it was thought that such a number does not exist till the solution of cubic forced mathematicians to introduce them. And what was the argument? Just like this, proof by contradiction. Minus 1 is, any number is the square of its square root. So minus 1 is square of its square root. So minus 1 is root of minus 1 into root of minus 1. Now apply this rule. Then you get minus 1 is root of 1, but root of 1 is 1. So there is a contradiction. So, but don't we, have we not now accepted root minus 1? How we account for it? You apply suitable restrictions on the use of the rules. So, similarly, can we not conceive of fractions x by 0 with suitable restrictions? Indeed, in some areas of modern mathematics, versions of 0 are indeed adopted through suitable euphemisms or formalisms. So, euphemisms are adopted in calculus and formalisms in algebra. And therefore, we should question ourselves that should we not refrain from saying that the ancients who did not follow our convention committed errors. It is like my religion is valid and all other religions are wrong. Take the area of commutative algebra. There is a concept of ring of fractions. For any multiplicatively closed subset S of a commutative ring, one constructs a new ring S inverse R where elements of S become invertible. So by introducing fractions of the form A by B, where A comes from R and B comes from S. And S is allowed to include 0. But what happens is, if 0 belongs to S, then all elements in the extended ring become the 0 element of S inverse R. So in particular, we have 0 by 0 equal to 0. So these things are from the subject which I teach in MSc, sometimes in BSc, in the mathematics course. It comes at the very beginning, localization. 0 by 0 there is called 0. In fact, A by 0 is 0 for all non-zero elements in A. So what I'm trying to say is, here is an instance of rigorous formal modern mathematics which permits fractions with 0 in the denominator and accommodates expressions like 0 by 0 equal to 0. However, those who are into this mathematics, they will say, look, the ring S inversa does not have Reed structure. It is really a trivial ring, consists of only one element. But I'm just saying that this notation, you can see this notation in a modern book. Now, in modern theory of abstract integration, not the way it is done in BSc, it is through measure theory, a close analog of Brahmagupta's rule 0 by 0 equal to 0 is used in a more substantial way. So now I'll show you in measure theory. So setting infinity is 1 by 0. For convenience, the rule 0 by 0 equal to 0 of Brahmagupta may be envisaged as 0 into infinity is 0. Precisely the modern convention adopted in measure theory and probability. The most famous book in measure theory, one of the most standard books is Real and Complex Analysis by Rudin. And I am just quoting, you don't have to understand measure theory or probability theory, etc. Just see what is written in a page of Rudin's Real and Complex Analysis. Let us define. He's just defining. You cannot just question that. These are our axioms. So he gives a rule. A plus infinity is infinity. A dot infinity is infinity. 0 into infinity equal to infinity into equal to infinity times 0 is 0. So just interpret infinity as 1 by 0. Then it is 0 by 0 equal to 0. It is written in a modern book. Now, this is all quotation from Rudin. It may seem strange to define 0 dot infinity equal to 0. However, one verifies without difficulty that with this definition, all the commutative, associative, and distributive laws hold without any restriction. The cancellation laws have to be treated with some care, just as your cross multiplication. So, A plus B equal to A plus C implies B equal to C only when A is not infinity. AB equal to AC implies B equal to C only when A is not infinity or A is not 0. So, if A equal to 0, there lies a problem. So, don't cancel when A is infinity. Just as you don't cross multiply when 0 is in the denominator. So, this is from a page in analysis book. Now I'll take you a page from algebra book. You know Bourbaki. Bourbaki is abused because of being too formal in mathematics, too rigorous, too formal. It is almost, painful. So in the rigorous book of Bourbaki, you look at what is written. So that is something called valuation theory, which is absolutely fundamental in commutative algebra, algebraic geometry, and algebraic number theory. So there, take K to be a field. Field means, collection of rational numbers or collection of real numbers or collection of complex numbers. Take K to be a field of complex numbers. With that, you add infinity, a symbol. And then the laws of composition of K extend to this new number system. A plus infinity is there, so they are defining all this. And then the last line, this is written in Bourbaki, I am not changing anything. 0 inverse, that is 1 by 0 is infinity, and infinity 1 by infinity is 0. It is typed, printed. Bourbaki's commutative algebra book has this symbol written there, just as Brahmagupta and Bhaskaracharya has done. Mind you, I am not saying that Brahmagupta and Bhaskaracharya knew measure theory or valuation theory. What I am saying is the conventions they adopted for which they are criticized are precisely the conventions which are used in measure theory and valuation theory. Now, what was the ancient Indian thinking about division by 0? Unfortunately, they never elaborate their thoughts. So, we will not be knowing that, and that is not regarding division by 0, about everything. As Bhaskaracharya says, what is the necessity for details for the intelligent student? A mild instruction suffices, etc., etc. So we don't really know that much detail, so we have to imagine. But the whole point is that whatever they're written, there's nothing unsound about it. Also, the rules on division by zero in different ancient Indian treatises are not always the same, just as modern conventions also differ. In the book of Rudin in measure theory, you saw the convention 0 into infinity is 0, because that will be needed. Whereas in valuation theory book, 0 dot infinity is undefined. So similarly, in ancient India too, there would be differences. One thing I have to remember, because I am repeatedly telling that you may have to remove your specs of calculus while reading the algebra books of ancient Indians. It is usually in the sections on algebra that rules on division by zero occur. And Professor Sathe, who will be lecturing on another topic, he has remarked in one of his articles that algebra, he describes algebra as the first bold adventure into the unknown. Now, it is not that ancient Indians did not know that there are difficulties in putting zero in the denominator. That is why, just as division by zero is forbidden in modern basic mathematics, it was forbidden in ancient Indian arithmetic. They are very clear about it that this is a concept for higher algebra only. Because Narayana makes this distinction very clear here in Patiganita, basic arithmetic. Division by zero is not recognized. And you say that they did not know that you cannot do division by zero. And it is not mentioned here. It is of use in Bijganita. So I have mentioned division by zero in my Bijganita. They are very clear about it. And modern historians try to interpret ancient Indian verses on division by zero in the light of calculus. Some of the verses then appear imperfect, flawed expressions of calculus principles, and some appear as absurd errors. And the picture changes in the light of algebra, as shown by Professor Sathe had made an analysis of some examples of the algebra treatise of Bhaskaracharya. And you have to keep in mind that some of the statements on division by zero in the general text can be interpreted in the framework of both algebra as well as calculus. And there, the division by zero closely resembles the treatment of infinitesimals by Newton, not the treatment by Cauchy. And there's another statement of Nagarjuna that a wrongly perceived shunyata ruins a person of meager intelligence. It is like a snake that is wrongly grasped or knowledge that is wrongly cultivated. So they're fully aware that zero can be problematic. So now I'll talk about Professor Sathe's model. So Bhaskaracharya defines two terms, khaguna, a number with zero as multiplier, and khahara, number with zero as divisor, as algebraic objects. And to distinguish between zero and that special number, we introduce a notation for our convenience, that epsilon, let us call epsilon to be multiplied zero, and infinity for 1 by 0. So Bhaskaracharya apparently has three kinds of numbers: the usual numbers, the multipliers of this epsilon, and the multipliers of the khahara, of infinity. So this multiplier, this real number into infinity, that is, or this entire collection is called khahara, and the rules are x epsilon y times infinity equal to xy. So these are understood. It's not the way Professor Sathe is saying, it's not very clearly spelled out in the ancient text. And at the end, epsilon may be identified with zero. The khaguna, so khaguna is like zero, has the quality of zero. So it is to be identified with zero at the end. Now, Bhaskaracharya's Lilavati is not a book in algebra, it's a general text. So there, the way he introduces these terms can be interpreted in both ways. The epsilon can be interpreted as an algebraic object to be put to zero at the end of all operations. On the other hand, it can be also interpreted as an infinitesimal t, where t goes to zero, as in Newton's fluxions. And his illustrative exercises to go well with both. But it is his exercises in Bijganita, which by the very definition is algebra, they admit only the algebraic approach. And you should remember that Bhaskaracharya talks about applications in astronomy only in his commentary on Lilavati. In his commentary on Bijganita, nowhere he talks about applications to astronomy. So there is no calculus in his verses in Bijganita. So he defines the zero divided number is Kahara. So there, Bhaskaracharya, he talks about these rules. Number x, 0 multiplied becomes 0, but the consequent Khaguna must be retained till the end. So it is something like this, that what we actually do, we are taught of lot of formalism, but we actually, everybody thinks like this, that this, the so-called limit when x tends to 0, what we do is that we don't assume x equal to 0 and go as far as we can, and at the end we put x equal to 0. But this basic thing we talk about in a lot of euphemisms, and there they boldly say that this x is to be interpreted as x tends to 0, that is, it is something like 0, but you should not put it put x equal to 0 except at the very end. So what we do usually in calculus, without saying so, that is formalized here. And this postponement of evaluation is which is done, which it is actually formalized in algebra, modern algebra. So for example, there is something called operations modulo p. So like 21 and 3, these are 0 modulo 3 because they're divisible by 3. But 21 choose 3, that is 21 into 20 into 19 divided by 3 factorial. So here both the, you see 0, 21 is also 0, 3 is also 0. But 21 choose 3, that is not 0. What happens is the identifications 21 with 0 and 3 with 0, they are made at the end. First, you treat 21 as the usual integer. And finally, so this is, you cancel 3 with, so it is 7. And 7 is modulo 3, this is 1. Then you again cancel this. So this is 10, which is again 1. And this is of course again 1. So the whole thing is actually 1. Now this is something which there is no limit calculation. It's algebraic substitution, which is done in modern algebra in characteristic P. And that is the kind of mentality which Bhaskaracharya has been showing. And for instance, I think, let me just skip a few slides. So this is a famous, yeah. Hello?
Can you complete in 3-4 minutes?
Yes, that is what I'm targeting. That's what I'm targeting. That's why I'm skipping some slides. So there is a famous line of Bhaskaracharya, which interpreted would be this x infinity plus y is x infinity and so on. And this principle can be seen in the extended real line of analysis, measure theory, and the theory of rank valuations. Now, if you see Professor Satte's interpretation, then it would be x infinity plus y is x infinity, which can be seen in the study of higher rank valuations. Now, these profound things, people make fun of that with such idiotic statements. Like Connor and Robertson, they write very well, but on this issue, they write this kind of thing, and the people in India, they pounce upon it, they copy from there without acknowledgement and write in journals of science education. It's very unfortunate. And the example which I was talking about, see, that has to be interpreted in the light of something called idempotent. E square equal to E. In that light, the things just fall in place. So this example which I was talking about, this has to be interpreted like this, that this x infinity plus this number, this has to be taken x infinity. That is by the rule which I was, that famous rule of Bhaskaracharya, then squared, it will be x infinity times x infinity is x square infinity. So this whole thing is x square plus x times infinity. So when 0 multiplied, that is by with 0 multiplied is not the usual 0, that is this special, this epsilon. So the whole thing is x square plus x into infinity into epsilon is x square plus x. So, and infinity into epsilon, that is 1. So what Bhaskaracharya is just asking is eventually with this simplification to solve x square plus x equal to 90. A very reasonable problem. And you know what is the solution of that. So what I'm saying is that with the correct interpretation, and one of the rules is very clearly stated by Bhaskaracharya, that you have to adopt this rule that something added to Kahara doesn't change the Kahara. That has to be adopted while doing those exercises in Bijganita. So, people, those of you who are interested, you can contact me. And probably I'll give a 1-hour lecture in near future where I'll, show all the slides. So I think I'll just close with a quotation from Mahalanobis, P.C. Mahalanobis, that he talks about what Ramanujan was telling him, which he didn't understand. So I'll just, you just look at the blue colored thing. So Ramanujan looked on the number infinity as the totality of all possibilities. So this tallies with what Sate has been saying, that you take one infinity and then look at all its real multiples. According to Ramanujan, the product of infinity and 0 would supply the whole set of finite numbers. So again, that rule, x infinity into y infinity, epsilon into y infinity is xy. And with that, you can get all the finite numbers. Now, this, of course, has metaphysical meaning also. But the point is that these calculations of Bhaskaracharya, which is implicit in Bhaskaracharya, that is very likely that Ramanujan was talking about those things to Mahalanobis, and Mahalanobis did not understand. So maybe I'll stop.
Okay, Amartya.
Yeah.
Can we have the questions at the end? You know, we are running a little late, but we
I should. Yeah.
Is it okay? We may have it later.
Yes. I'll be attending the whole session.
Okay. See, for instance, I don't know what Professor Avinash Satai will do. If he doesn't join, then we'll have more time. Yeah.
Okay.
Okay. So now I will. Now Professor Arvinda has to present his talk. Before that, I will introduce Arvinda. Arvinda, are you there? Arvinda?
Yes, I am there. Correct. I am there. Yeah, I am there.
Arvinda, Professor C.S. Aravinda, he did PhD in TAFR in Mumbai, and now he is a faculty member at the TAFR Center for Applicable Mathematics in Bengaluru. His main research interest is in geometric, dynamic, and topological aspects of negative curvature. He translated the famous book Ramanujan, The Man Who Knew Infinity. Most of you would have heard about it, the famous book by Robert Kanegel. So he has translated this work into English, Kannada, English work into Kannada. Professor Arvinda is the chief editor of Bhavana, the very popular mathematics magazine, and which has a very big outreach. And it is an outreach effort for the curious, the interested, and the cognoscenti, as he says. Over to Professor Arvinda. Over to Professor Arvinda.
Yeah. Thank you. I am just trying to share the screen. I'm trying to share the screen. Yeah, are you able to see my screen?
Yes.
Okay, it went into some other page. Yeah. Is everyone able to hear me and see the screen? Yeah, can I continue?
No, we can hear you, but we can't see. Can anybody see the screen? I can't. Yes, we can see the screen, Arvinda. Yes.
Okay. So shall I go ahead? Yeah. Okay. Thanks a lot. Thank you so much for inviting me to speak in this session. I must make a confession. Unlike other speakers in the symposium, I am not a historian and I am really a novice. So this particular talk should be seen more as a sharing of my, or more like a student than a, somebody who is who knows about the history of mathematics and so on. So my tryst with Bhavana started with basically a lecture by Amartya Kumar Datta. So I owe this whole entire talk and the knowledge about Bhavana to him, which eventually inspired me to kind of name the magazine that we started Bhavana. So let's see what Bhavana is about. And I use this opportunity also to kind of reflect upon different ways of looking at, reading, not different ways, I mean, how one should read Sanskrit text, maths from Sanskrit texts. It's not enough if you know only mathematics and not Sanskrit. And it's not enough if you only know Sanskrit and not mathematics. And so in a sense, you need a knowledge of both. So I want to reflect on some of those points with specific examples. So with that, so let me start. And okay, this is my first slide. Actually, I want to dedicate this talk to Professor Rodhan Narasimha, who passed away just about a few days ago. And I dedicate this to him because, I mean, he also inspired me to kind of look at, we often Indians, we say we do not know Sanskrit, but his contention was that most Indians, Indian languages have an influence of Sanskrit. So we do not know that we know it. So he inspired me to do this. So I thought I should really dedicate it to him. And while after dedicated to him, it's not just that he said something, but I mean, I want to start with an example. Rodhan Narasimha himself wrote an article in Nature almost exactly 19 years ago, in 2001 December, in the famous magazine Nature. So in that magazine Nature, in the one-page article, he actually discusses one verse from Aryabhatiya. And that's what he discusses. And then the particular thing, if you just look at read this verse, it looks as if one is not one is talking some nonsense, some gibberish. But then, I mean, if you look into the way the numbers are associated with certain names and letters in the Indian culture, so you can actually discern a table for the sine function. So that's why he calls this article, the title, he titled the article as Science in Terse Verse. So the verse is terse, so that's why. And I thought I'll just quote a quotation from Karl Weierstrass, who says, mathematician who is not something of a poet can never be a complete mathematician. I was quite amused by this statement initially, but now I understand that in mathematics also, when we write a paper, we are not supposed to write anything unnecessary. We are succinct, almost like a poem. Poets, use appropriate words, and there is something like succinct, expression. So in a sense, I think in that sense, one has to be a poet in the sense that we should know to express things in brief. And in Sanskrit culture, perhaps they took it to a very great extent because the time and the amount of knowledge, almost like, sort of, compressing a file into 1 GB kind of thing. So the compression was also, but everything had a very great system. So this is a slide basically from that article, and not from that article, but this slide is formulated out of that article. So after this brief introduction, let me come to the main topic. So the topic was Brahmagupta's Bhavana and reading mathematics texts, right? So, so what I'm trying to say here is that, okay. So I think I can't see my screen, so let me just keep it like this. Okay. So Brahmagupta Bhavana, we kind of Amartya also mentioned this, and I prefixed it by Manuel Oyanguren's monograph. What do I mean by that? Manuel Oyanguren is a Swiss mathematician, an algebraist, and in a monograph that he wrote titled The Witt Group and the Problem of Luroth. So it looks like completely no relation to Indian mathematics, but the 5th chapter is titled Also sprach Brahmagupta. Basically, that means in German that thus spake Brahmagupta. So what did Brahmagupta say? So in that particular chapter, he starts with this one, on the right side where I'm showing my arrow, it shows a Sanskrit verse, and then in the exposition he actually writes, I'm this kind of lemma. He calls Brahmagupta's lemma. So I'm zooming that particular part in. He says in the chapter 8 of Brahmasputa Siddhanta, I think, Brahmagupta proves the following lemma. And Brahmagupta, let's see who he was, when did he live, and so on. And it's amusing to see that Brahmagupta proved this lemma in this modern notation. And the crux is the last line. Here you would notice that A appears here, A, here. So 3 places. So in the sense of sort of S comma T and X comma Y are very similar expressions here, S squared plus 8t squared and X squared plus AY squared. And there is a rule to combine it and get something like this plays the role of S and this plays the role of T. You can say get a number of very similar sort. So this is the identity. This is called the Brahmagupta identity. So, well, Brahmagupta, I don't know how he looked, in the sense that he lived, in the early 7th century for about 70 years. And this is an artist imagination of Brahmagupta. Just as in mathematics, when you say a variable, we give a certain symbol. Let's think of Brahmagupta symbolizing this image. We do not know how he actually looked, perhaps. This artist imagination. Okay. So what is Brahmagupta's Bhavana? So Bhavana is a Sanskrit word that was used by ancient Indian algebraists, as Amartya mentioned, to name a principle of composition introduced by Brahmagupta. And composition, of course, I talked about poetry, and you compose some way. Here you compose something else in mathematics. So in mathematics, a law of composition combines two composes two mathematical objects of a certain type to produce a third object of the same type. Something like, if you take two, let's say, natural numbers 2 and 3, you add and you get another natural number, namely 5. So that's called composition. You take two things and compose them and get a third one of the same type. So in the verses 64 and 65 of chapter 18, as Anguran mentioned, titled Kutakadhyaya, of his magnum opus work called Brahmasputa Siddhanta, also mentioned by Amartya in his talk, Brahmagupta discusses the problem of finding positive integer solutions to a certain quadratic indeterminate equation. So while describing the roots obtained by his rule, Brahmagupta uses the word kritam, as we will see. So this is the first page of this book, Brahmasputa Siddhanta. Anybody can find, it's in Wikipedia. When you see this is available free for anyone. And I downloaded from there to get to the actual verse and the whole work, not just the particular verse mentioned that. So this is a book, as we see, published in 1902 of Brahmasputa Siddhanta and another work of Brahmagupta. And it's edited with commentary by Sudhakara Dwivedi. So the tradition of when you transcribe and writing commentary seems to be quite you can see it's a continuous pattern. It's not just there is any gap in Indian culture. So this is and it's thanks to the University of Library Chicago, who have actually completely put it in digital form available for everyone. Okay. So let me zero in on that particular verse that Anguran mentioned in the beginning of the chapter. And that particular section is called Varga Prakriti. Varga would mean square, and Prakriti, you can think of it as square nature. Atha Varga Prakriti, which means we'll now discuss the square nature. And the verse that I never elaborated on, let me just read that verse, because that's the hero of this talk, my 30-minute talk. So the verse reads like this. Let me read Sanskrit for those who may not know what Sanskrit is, or how to read Sanskrit. Moolam dvidheshta vargat gunaka gunadishtayuta vihinacha adya vadho gunaka gunaha sahantya ghatena kritamantyam vajra vadhaikyam prathamam prakshepaha kshepa vadha tulyaha prakshepa shodhaka hrite mule prakshepake rupe. So verse 64 and 65, maybe in some transcriptions it was 65, 66, even that is written in the book very clearly. So you can see the meticulous nature, and the commentary is written in Sanskrit. I'm not going to read this. I'm just going to say that the tradition is that, you really kind of looked at what was there before and understood in your own way and wrote an exposition, you can say. So these are the two, this thing commentary. At the end of the commentary, this is Sudhakar Dwivedi's commentary. And this Varga Prakriti is also called Kanishta Jeshta, and that's what he mentions here. And he ends that commentary of those two verses by saying, Atra Upapatyarthe Matkrita Bhaskara Bija Tippanyam. Bhaskara refers to Bhaskaracharya, Bija refers to Bija Ganita, the notes of Bhaskara, and Varga Prakriti, and he has just says Utpattir Vilokya. So he says, I mean, his take on the Bhaskaracharya's commentary. Basically, sometimes they may just be copying, because transcription you just copied, but if you had a new insight, they would add, I think. That's the tradition. So let me just get to the shloka. So what I'm trying to say in this particular talk is, where is Manuel Vayanguryan's version says Brahmagupta's lemma and that particular identity with S, T, X, Y, and so on that you saw, and where is this Sanskrit verse that I just read out, and how do we kind of connect the two things? Okay, so in Sanskrit tradition, when you are a student of Sanskrit, so when you see a verse, first of all, you look at that. First line is Moolam Dvidheshta Vargat Gunaka Gunadishta Yuta Vihinacha. This is how it appears in poetry. But then to understand, you break it into words. Break it into words meaning Sandhi, Dvidha, and then arrange it in an order like a sentence. So the beauty about Sanskrit is you can put the words here and there, but the grammatical rule makes the whole expression really unique. So I have split, and the first line looks like this. If you want to read it in a textual manner in an order, Dvidha Vargat Ishta Gunaka Gunat Ishta Yutacha Vihinat Moolam. So what does it really mean? Dvidha, Dvi means two, Dvidha means like Vividha, we say for variety. So Dvidha means two types. You have to take two types. So let's just take two types of numbers, let's say x1, x2 in modern notation. Vargat, Varga means taking their square. So take the squares of these two. And then Ishta Gunaka Gunat. Gunaka means product. Guna means product. Gunaka is the number with which you take the product, and Ishta means a certain chosen number. So multiplied by a chosen number. Here, let's take that number, the chosen number to be capital N. So if you multiply these two by capital N, you have these two, and then Ishta Yutacha Vihinat. Again, you take a chosen numbers and add or subtract. Yuta means to add, and Vihinat means to subtract actually. So here he very clearly mentions add or subtract. So to which you add or subtracted the chosen number. So you have n x1 squared plus or minus m1, n x2 squared plus or minus m2, and then you take moolam of that. Moolam means varga moolam, that is square root. So you take the square root of this whole thing expression. So in a sense, the gist of the first line, if I just write it almost as a line, like each word to word meaning, because this is how it is tradition. You take the word to word meaning, pratipada artha we call it, and then write the tatparya. So I'm writing the tatparya, first line. It says, if you take two triples of numbers, x1, y1, m1, and x2, y2, m2. So that's what we did, right? And are taken such that for a given n, you look at this expression. y1 equal to this, y2 equal to this. I'm just coding it by I, for I equal to 1 or 2 in modern notation. You take n xi squared plus or minus mi is equal to yi squared. So this is what the gist of the first line is. The second line, Adya Vadho Gunaka Gunaha Sahantya Ghatena Kritamantyam. Adya means first, the first two. You take the first two. Vadho means to hit or kill. And in Sanskrit, Vadha, Ghata, Hrita, Hara, everything meant product actually. Multiplying two things. Okay. Because it gave you power. It's more specific, very clear when you use the word Ghata for power. So you needed power. So you got power by multiplying, right? So we say united we stand, we say. So multiplication gives power. So it has a definite reason why the word is used for multiplication. Adya Vadho, you multiply the first two, and then it gives you x1, x2. Then Gunaka Gunaha. So Gunaka, you remember capital N, and then you take the product with the n, and you get n x1, x2. And then what you do is Antya Ghatena Saha. So here Adya meant the first, what you started with x1, x2. Antya meant, in the first line I ended with yi. So Antya is y1 and y2, and you take the product Antya Ghata. So you take the product, so y1, y2, and then you Saha, meaning you combine them, which means you subtract or add. So you get plus or minus y1, y2. So if you do that, nx1, x2 plus or minus y1, y2, you get Antyam Kritam, which means you get the analog of y1, y2. Okay, Kritam means accomplished. So the second line just is y, the new whatever, I mean, instead of y1, y2, composition, you composed things and you got this y is equal to n x1, x2 plus or minus y1, y2. And what is the third line? So each thing is so interesting, so rich actually, in the sense that, so the third line was Vajra Vadhaikyam Prathamam Prakshepaha Kshepa Vadha Tulyaha. Right, that's what we saw. The beauty is the following. So Vadha we saw is the product, right? Product. Vajra Vadha. So what is very interesting is we started with x1, x1, x2, y1, y2 we got, right? We started with x1, y1, x1, x2, and y1, y2. So Vajra Vadha means product. Vajra means cross product. So when you cross multiply, so you had x1, x2, and y1, y2. When you cross multiply and then Aikyam, you combine them. Vajra Vadha Aikyam. So you take x1, y1, x1, y2, x2, y1. So it's so beautiful that, I mean, you take a cross multiplication, add in just one word, Prathamam, which means you get the first one, that is x. So when you compose these two things, you get x like this. And then Kshepa Vadha. Kshepa is the remaining thing. So you take the Vadha again, this product. Kshepa Vadha is m1, m2 is equal to Prakshepa Tulyaha is equal to m1, m equal to m1, m2. So this is what the third line says. So the first three lines now are enough for me to talk about Brahmagupta's lemma. First three lines may be now summarized as follows. For a given integer n, if two triples of whole numbers x1, y1, m1 and x2, y2, m2 are taken such that they satisfy this equation that we start, the first line said this equation, then the triple that I mentioned x, y, and m obtained by the above clever composition of the given two triples also satisfies this same rule. Nx squared plus or minus m is equal to y squared. And I'm not doing the last line because first of all, the verse is terse, and the last line requires some more effort on my part to understand, which I haven't really kind of completely followed in the sense that to my satisfaction. Of course, I mean, people have understood and written commentary. So, I mean, it's just that I haven't not understood, which is why I made a, declaration at the beginning that, I'm just understanding this. Anyway, so Sudhakar Dwivedi in his commentary, he says that the second part of the verse, meaning the last line of the verse 65, deals with what is called Thulia Bhavana, where you take the Adyas, the first two to be identical, and Antyas to be identical and Kshepas to be identical. For instance, if the Kshepas, M1, M2, you take it to be 1, so then you would be looking at what is called, we'll see an equation, in my next slide. So that is what is dealt with in the last line. And as also noted by him, the above explanations of these rather terse verses of Brahmagupta are in consonance with what is discussed in the later literature, such as may be found in Bijaganita of Bhaskaracharya. So there later, between Bhaskaracharya's commentary of this Bhavana and Sudhakar Dwivedi, there are a lot more, Udaya Divakara, Jayadeva, and such people. Okay, so this is Brahmagupta's lemma. So now I'm trying to kind of read from Sanskrit, and now I'm trying to connect back to Vayanguran's statement of lemma. So anyway, I don't have to repeat. I just said this several times. So this is what is gotten. So you'll, instead of when you take the identical kshepa, that is m1, m2 equal to 1, you are actually looking at this equation nx squared plus 1 equal to y squared, and you want to look at the solutions of this for a given n. And so if you take two solutions of this, x1 and y1, there is no m now, right, because of 1. If you take x1 and y1 and use this composition x1, y, and x2, y2, if you take and compose it this way, given by the recipe given by Brahmagupta, you get this, and this is called Brahmagupta identity, and this is the form in which Vayanguran stated. Only difference is Vayanguran took y1 squared plus nx1 squared, y2 squared plus nx2 squared, and he got And then naturally there will be plus here, and he got minus there. That's all. That's the only thing. As we saw in Brahmagupta's Bhavana, the plus or minus versions are both there. So it tallies with Wanguran's statement of this thing. So he was not really pulling out the first one saying that, okay, I mean, saying something. So there was actually exact method and reasoning and so on. So this is Brahmagupta's lemma, and using that Brahmagupta's recipe, that particular equation n x squared plus 1 equal to y squared for a fixed positive integer n was later called Pell's equation. Actually, even Pell was wrongly named, as history knows, and in modern Europe. Since Brahmagupta is arguably the first mathematician to investigate this important equation, so we call it Brahmagupta-Pell equation. So for more on this equation, Amartya Datta has written a very elaborate and beautiful article in the magazine Bhavana that was already mentioned by Sriram in the inaugural issue. I'd like you to take a look at that. So in that particular article, Amartya also mentioned the in-between commentators called Jayadeva and so on. And then he says Jayadeva, all the recipes and so on, he says that till any new evidence is found, we may regard Jayadeva, one of the intermediate commentators, as the first mathematician to have completely solved in integers the Brahmagupta-Pell equation. And in his treatise Bijaganita, Bhaskaracharya himself gives a lucid exposition of a variant of Jayadeva's method. Jayadeva was before Bhaskara. Method, illustrating it with a difficult examples like capital N equal to 61, capital N equal to 67. For these cases, they write down the solutions there. And as Amartya mentioned also in his talk, so when for N equal to 61, what is interesting is that Bhaskaracharya has given an explanation solution, and later the problem is posed by Fermat almost 500 years later with N equal to 61 itself. That's an interesting observation. Applying Brahmagupta's recipe to obtain the integer solution, Jayadeva perhaps arguably the first one who obtained the solution. So for N equal to 61, it gives a positive integral solution. The solution you would see x is equal to such a large number and y is such a large number. So for N equal to 67 itself, the solution is quite large. I say yes, the large numbers indeed, and no less. So one had a facility to deal with such large numbers and obtain solutions, complicated stuff and so on. I refer you to this article, and it's available in this website. Again, it's available for free. No, you don't have to do anything. You just go there and navigate, and you will be able to get Amartya's article. Okay, so now for the rest part of the talk, so this thing on Brahmagupta's Bhavana is more or less over, but the second part of the title, I said reading maths from Sanskrit. So let me dwell on it a little bit and give some examples. Again, it's not like I am kind of promoting Bhavana. It's just that, Bhavana, we have covered many of these historical aspects. I thought, it's a good point for me to say, dwell on that. So P.P. Divakaran, basically a physicist. He taken a lot of interest in Kerala's this thing, what he calls the Neela School of Mathematics, and done a lot of work, and even written a book on history of Indian mathematics. And that book has been reviewed in Bhavana by Avinash Sakhe. So all well-known people and people you have heard in this symposium. So in the October 2018 issue, Divakaran wrote a Bakshali manuscript article. He kind of says that, he actually says that the decimal system of representing numbers in verbal notation is already present as early as Rig Veda, actually. So I'm not going to read this for want of time or in the interest of time. So what he says is that the entirely Vedic solution to represent a problem was to spoken identity to every number. This involved the following steps. First, you give the names to numerals up to 9, the oral analog of the familiar symbols, Eka, Dvi, Tri, Chatvari, like that, up to 9, Nava. Then give names to powers of 10, Dasha for 10, Shata for 100, Sahasra for 1000, Ayuta 10,000, and so on. Then combine the names of the coefficients Nj. This is basically polynomial algebra in play, which we know very well. The coefficients and a1x1 plus a2, a0 plus a1x1 plus a2x squared and things like that. Here you can take x to be 10, and in the polynomial notation you write these numbers. So that's what we do now. How did they do in Vedic this thing, where they did not have any symbols and so on? So in the verbal notation, how did they do? They use these names, and following rules of Vedic grammar, they composed two names to implement a mathematical operation of multiplication, then invoke another grammatical rule to implement the operation of addition of such individual terms to finally arrive at the name for a number n. And let me just give an example. That, I mean, these are all, I'm quoting from Divakaran's article, so I'm not writing anything myself. So in illustration, Divakaran actually mentions this particular number 60,099, and this number occurs in Rigveda itself, yeah, in the first mandala actually, Rigveda. And how is this number read there in Rigveda? It says Shashtim Sahasra Navatim Nava, and Divakaran says separation of words matters. So you remember he mentioned one very grammatical rule for operation of multiplication, another grammatical rule for addition. So what do you mean by here? When you say Shashtim means 60, Shashtim Sahasra, the separation of words, that basically means it's a multiplicative. Vedic grammatical rule tells you have to put a multiplicative rule, which means 60 into 1000. So that is 60,000. And then Navatim Nava, and then you may say again a gap. So why is this gap there? Again a multiplicative notation? No, the thing is that the word for 1000 is Sahasra, but here you see Sahasra in the sense that it's a what's called a dirgha syllable, long syllable. That means that you have to get an additive notation there. And Navatim Nava, there is no separation. So 90 and 9, 90 plus 9 is 99. So these two are additive notation in Vedic grammatical rule. And the first one, Shashtim, is for 60 and Sahasra is for this thing. So that's how they actually did this. So the verbal nomenclature was already there, and then slowly things evolved. So now I quote another article in Bhavana, and this is an interview of a very famous historian called Radhacharan Gupta, who lives in Jhansi. So he's 85-year-old, and I went to Jhansi to interview him. And in the interview article in the October 2019 issue of Bhavana, so people might say, well, I do not know Sanskrit, so I won't work in these kind of things, or I may not be interested. But if you are a mathematician and really say, I mean, come on, let's see how Sanskrit people have, how people have expressed mathematics in Sanskrit. If you only have the curiosity, then actually you can pick up things. And this is what Radhacharan Gupta himself says. He says he did not know Sanskrit. So I read dictionaries of Sanskrit. When we want to read a paper in French or German, we make a lot of efforts to read dictionaries and understand. So why not do it for Sanskrit? So that's what he did. And he's basically, Radhacharan Gupta is a student, PhD student of Saraswati Amma, another well-known historian from Kerala, whose book, Geometry in Ancient and Medieval India, is a classic now. It's reprinted by Springer. And Radhacharan Gupta did her PhD with her. And so he says that, he did not know Sanskrit. So he referred to many books and consulted her. And in fact, he also he says, let me just read, I think. I quickly made myself accustomed for doing this kind of research work. At the same time, I looked at many Kannada, Tamil, and Telugu works and got the opportunity to consult them. Saraswati Amma's mother tongue was Malayalam. So it was surprising for her when she checked my Sanskrit translation and praised it by saying, Gupta, your translator are quite accurate. I was able to translate many untranslated stanzas. So what I'm trying to say, I just mentioned the example of reading papers in German, French, Italian. I mean, Radhacharan Gupta took on the Indian languages, which also kind of definitely in their core have can capture the sentiment of Sanskrit and expression, poetry, and so on. So he actually consulted those and tried to get the right interpretation. He says many things had not been interpreted correctly, and though I don't say that I am an expert in Sanskrit, I could pick up some technical words and I was able to arrive at many correct interpretations. And here is an example of one of his correct interpretations later. For example, in Sanskrit, a sentence may translate as he was killed by the king. Okay. And then some Sanskrit scholars may not know that the mathematical meaning is it was multiplied by 16. So we have already seen killed, vada or hata is multiplication. So there is no problem there. How does king get this thing 16? So because the word rupa in Sanskrit is used for 16. So it's not a kind of a, what should I say, an arbitrary name and number. There is definitely a tradition. It's imbibed in the tradition. And he goes on to say there were hidden numerals, and hidden numerals called Bhuta Sankhya. And it again comes from the tradition. For instance, Surya, the sun, is used for 16. I mean, he has 7 horses, but they're only the race. And these things, again, something called Amarakosha tells you that Surya, one of the synonyms for Surya is Dwadashatma. Dwadashatma means the heart of the thing is 12. And Chandra, we know, is only Bhumi had only one moon. So that one is Bana, arrow. Here, this is called Panchabana. Again, Amarakosha tells you what are these, Aravindam Ashokancha. One of the Bana bears my name. Okay, Navamallika and so on, Nilotpala and all that. There are 5, this thing for Bana means 5. And Sagara, 4. I mean, in our tradition at home, when we prostrate before elders, we kind of recite something and we start with saying Chatussagara Paryantam. So we know that Sagar for 4. So similarly, the word eye, Netra, you have 2 eyes. So Netra is for you 2. And Netra is not the only word for 2. Ashwini, the twins, is also used for 2 and so on. So you have a lot of variety so that you can express mathematical content in poetry. And if you are very aware of this culture, you can get to right interpretation. That's what Radhacharan Gupta did. And he also says, while Mahadeva's eyes, Shankar's eye is used for 3 because Trinetra, as we know. So the usage is all because of our Indian culture and tradition is tied to the language. So one needs to have an overall knowledge of these sentiments to effectively translate. So that's kind of what is very important. And so I want to, when we talk about overall knowledge and so on, I talked about music composition. I'm ending my talk. I'm just ending my talk. Can I take just 2 minutes?
Yeah, yes, okay.
Okay, 2 minutes, just 2 minutes. So the bhavana, the shloka that we saw. So now I'm just kind of Thank you.
Thank you. Stop sharing. Yeah. Is Professor Avinash Sathe there? Hello. Has Avinash Sathe joined? Has Avinash Sathe joined?
Checking, Professor. 1 minute. I'm checking.
Yeah.
I'm confirming. No, Professor. No.
I don't see him. Yeah.
So in that case, I suggest that for the next 7-8 minutes, we will have questions on Amartya Kumar Datta's talk and Aravinda's talk. We can, if anybody has any questions, now they can fire. because the other two talks are of a different nature. Okay. So please, you can raise your hand and ask questions on these two talks.
May I ask a question?
Yes.
I want to ask this to Amartya Bhaskaracharya here.
Yeah.
This example about the algebraic equation that you gave, a polynomial equation, if its intent was just to say that you solve x squared plus something times x equal to 63 of 1 or something, why introduce all those 1 by 0 and all that to complicate matters? What was the purpose of that?
Amartya to respond. Amartya, are you there? Amartya, are you there?
So he's not there.
Oh, Bhaskar. How are you?
Fine.
Good. Any questions to Aravinda?
Yeah, I just want to tell Aravinda, Bhaskar here. I found his talk very, very interesting, amazing. You can talk about Gauss equation in the poetry. It was great.
Very good.
Yeah, thank you. Bhaskar, I also brought in another music aspect. Indian classical music has a lot of mathematics, which is why I thought I'll put this verse into music. It's not my singing. It's a friend of mine called Giridhar who put it into music. And I wanted to say this because Ramanujan grew up in an atmosphere of classical music and his mother was a singer and so on. I thought I would
I know that
aspect. Thank you.
This is fantastic. Thank you very much. Wonderful lecture.
Good.
Thanks a lot.
Good.
Hi, Aravinda. This is Sophie.
Sophie. How are you?
Good. Very nice talk. Very interesting. Actually, I would have been interested in, in these slides if you could send them, or a paper if you have written on that.
Absolutely, I will be happy to send you the slides. You look quite different with your hat, I must say.
Because this is the fifth layer. The fifth layer of clothes I am wearing because of very loose.
Oh, acha.
Okay.
Thanks a lot.
Good. Any questions? Maybe, Amartya may be having connectivity problems. That is what I suspect, Okay, we'll come back, to Amartya, if he comes back, he will come back, but I think there may be some connectivity problem. So then, shall I proceed to the next talk? Next talk, I will proceed. Pai, are you there? Venkateshwara Pai?
Yes, I'm there. Yeah.
Very good. So now I will introduce Dr. Venkateshwara Pai. Okay? Yeah. Venkateshwara Pai, he did his PhD in Indian astronomy in IIT Bombay in 2011. Later, he worked in Shastra University, Tanjavur, and currently he is at IISER, Pune. He is the co-author of a book called On Karana Paddhati. Karana Paddhati was a work by Pudumana Somayaji. So he is the co-author of a book on Karana Paddhati with translation and explanatory notes and all that. This is a very important text of the Kerala school, and it has got, the main text is in Sanskrit and commentaries in Malayalam. So Professor Pai is an expert in both the languages. So in fact, he is the only person who can really, look at technical Malayalam texts and astronomy, okay, and actually make the correct interpretation. He is one of the only, I think maybe he's the only person. Currently, he is working on other texts on Kerala astronomy, particularly one work called Drupkarana. So this is a very major text. In fact, I am working with it. Okay, over to you, Venkateshwar Pai. Okay.
Hello.
Are you
Can
we can see
can you see the? Can you all see?
We can see your slides, Pai.
Okay. Thank you, Professor Sriram, for wonderful introduction. Yeah, you're all good evening, you all. So today I'm going to talk on continue in the Kerala school of astronomy. So, continued fraction is
go ahead. Yeah.
It is commonly referred to as value per sum is
Pi, you please unmute. Please unmute, Pi.
okay.
Let us wait for 2 minutes. There is some problem. Please be patient. Yeah. You have to press the proper button, Pi. Yeah. You have to share the screen, Pi. Yeah.
Yeah. So I'm just trying something. Can you hear me? Can you hear me?
We can hear you. We can hear you.
Okay.
Yeah. Please share the screen.
Yeah, that's yeah.
Yeah. Can you screen share?
I'm not able to share my.
Pi, then shall I talk and then you can give?
Yeah, sure. Yeah, sure.
Okay, 1 minute. Yeah. I will give my talk. So let me introduce myself. I am Sriram. I did PhD in physics from IIT Kanpur in 1978. That was in theoretical physics. And I was a professor in Department of Theoretical Physics, University of Madras for a number of years. Currently, I am the president of the Indian Society for History of Mathematics and also the Professor K.V. Sharma Research Foundation. I have worked in high energy physics and also on nonlinear dynamical systems. I have been working in the area of history of Indian mathematics and astronomy for nearly 30 years, and I am the co-author of many important Kerala texts, books on important Kerala texts like Tantra Sangraha, Yukti Bhasha, and Karana Paddhati, and I am working on continuing working on texts like Siddhanta Shiromani and Druk Karana. Last one will be with Pi. So okay, let me start sharing the screen. Let us see whether I will succeed.
Yeah, it is.
Okay, 1 minute, yeah. Let me start sharing the screen. Sorry, I also have a problem. 1 minute. Yeah, 1 minute. Please be patient for a minute. I will. Myself louder. Now I'm talking. Yeah, 1 minute. No, not this. Can you see the screen? Hello?
Oh, no.
Yeah, we can see the screen, but not your file actually. Yeah.
Yeah, yes.
Now we can see. Can you see the screen now?
Yeah.
Not yet. Perhaps it will take some time to load or something like that.
Yeah, maybe, yeah. Second order Taylor series, can you hear? See, I'm seeing in my screen.
No, in our thing, it only shows your screen with several PDF files. That's all. Yeah. I think we'll have to wait a little bit.
Yeah, you will have to wait because I clicked it. Yeah.
But no, have you said share also? I mean, meaning I don't know.
Yes. I have put your screen sharing. It says, yeah.
I don't know if others can, but I can't quite see.
No,
Okay,
Professor. We are also seeing only some PDF files.
Yeah. Okay, 1 minute. Let me try again then. Okay, sorry. Okay, I'm sorry.
No problem, Professor. No problem.
Yes, sir. You have to open that PDF file, then only it will be displayed.
Then I have opened it.
Yeah, it's not showing here. I think it. I don't know. It might take some time or.
Sir, I think instead of selecting the screen, you might have selected the folder, that browser, right?
No. You have selected the particular file.
No, that's where what is happening now, sir.
Try that one. Yeah.
You have selected the Explorer.
I'll be back in 2 minutes if you don't mind. This is somewhat unusual. Let me try again. Yeah.
Sir, you select the screen.
Yeah. Internet connection is unstable. It's saying 1 minute. Yeah. Let me see.
Sir, please stop sharing and then share again the PDF file.
Okay, 1 minute. Okay, stop sharing. Okay.
And now share the PDF file.
Yeah.
First open the PDF file and then.
Okay, I have opened. Yeah.
Okay. Yes. Now it is visible.
Yeah, now we're able to see. Yeah, we're not. Yeah, right.
Can you see it clearly?
Yeah, perfect.
Yeah, correct.
Yeah. Sorry for this thing. Yeah. Okay. So now my talk will be second order Taylor series for sine cosine functions in Kerala school. Okay. So now you see lot of developments in astronomy in the ancient times. Okay, both in Indian and Greek traditions anywhere had much to do with in mathematics. Had much to do with astronomy. Sorry, can you see? There's some problem. Pi thing is coming. Pi, stop it. Pi, can you stop it? Can you see this tree?
We can only see you now, but not the screen. I think you have to start. You have to share screen again. Looks like.
Yeah. 1 minute. Yes. Can you see now?
Yes, we can see.
Okay. Yeah. Yeah. Okay. So a lot of developments in mathematics had, close connection with astronomy. Actually, you will see that all the Indian astronomers were also mathematicians, like Aryabhatta, Bhaskara, Brahmagupta, Sridhara, Lalla. Okay. So like Vateshwara, and of course Bhaskaracharya too. You see, because mathematics and astronomy went hand in hand in those days. Now, the very motivation for introducing trigonometric ideas. Can you hear me properly? Can you hear me?
Yes. Yeah. Perfect. Go ahead. Yeah.
Very good. Yeah. The motivation of introducing trigonometrical ideas, whether in Greece or in India, was the non-uniform motion of the planets, as seen from the Earth. Okay. So now in this figure, maybe I'm not too good, but this figure is there. O is the center of the Earth. Okay. Gamma refers to a reference line called the Meshi. This thing, first points of Aries, called Meshagi. Okay. Now P0 is a planet. It's called a mean planet. It is moving uniformly around the center of the Earth. Okay. Now, but then it was observed that it is non-uniform. So for this, to account for the non-uniformity, they introduced a device called epicycles. Okay. In Indian astronomy, it is seen. Greek also it is seen. Okay. You draw a small circle around P0. The big circle has radius capital R. The small circle has radius small r. Okay. So now the direction associated called with the planet called Mandocha or apogee. This is the apogee in this thing. So now draw a line from P0 parallel to this direction of apogee and let it touch the small circle at P. Then P is the location of the actual planet as seen from the Earth. Okay. So theta T. Yeah. The true longitude is gamma OP. Okay. And the mean longitude is gamma OP0. Okay. Gamma OP and gamma OP. So the difference is, what we have to calculate, delta theta. I don't have too much time. We have to introduce a term called Manda Kendra, theta 0 minus theta A, the longitude of the apogee. So I will not go into details. It is just very elementary geometry. So what you get is, finally that OP also, it varies with the angle, but there is a peculiar assumption in Indian astronomy, very somewhat a different type compared to Greek. R by K is R by 0. So eventually, what I am saying is sin delta theta. Delta theta is the correction to be added. It is R0 by R into sin M, where M is theta 0 minus theta A. Okay. So the true longitude of the planet is given by the mean longitude minus sin inverse of R0 by R sin M. So this is how trigonometry came into picture. Okay. And Indians were far more, the Indian formulation is much more convenient. Greeks talked about chords and relation between chords and dots. Okay. And Indians work with half chords. And the Indian sign called Jya, you see, that is what is essentially the modern sign, except for a constant factor. Okay. So this is the motivation, and it is very important for what I am trying to say. Okay. So now, this is the picture. Okay. The true longitude will depend upon this thing, a trigonometrical function like this. So the theta t is the true longitude, theta 0 is the mean longitude, R0 is some stated radius, R is called Trigia, and M is called Mandakendra. Okay, and R0 sin M is called Bhujaphala, and R0 cos M is called Kotiphala. I'm sorry, I'm introducing a lot of terminology, but this is very essential for following the later portion. Now, if R0 by R is small, okay, then we can approximate it by theta t is theta 0 minus R0 by R sin M. Okay. So now, in our modern times, how will we do to get the rate of motion? So what we do is to find the rate of motion, you have to take the derivative with respect to time. Okay, so delta theta t by delta t. I mean, just to show that it is not the Indians didn't use the modern notation. They are not supposed to. I mean, it was in the ancient times. I just put capital delta theta t by delta t is delta theta 0 by delta t minus r0 cos m by r into delta m by delta t. Okay. So the true rate of motion is mean rate of motion plus a correction. Okay. So that is the main thing, and here this is what we have obtained from our modern ideas. But how did the Indians view it? Okay. In 950 CE, there was a text called Mahasiddhanta due to one Aryabhatta II. Okay, not Aryabhatta, the original Aryabhatta, but later astronomer. He says, Koti Phalagni Bhukti Gajya Bhakta Kaladi Phalam. You see? So this is, it expresses the whole thing in a very simple, few words. Okay. So he says that Koti Phala is R0 cos m. Okay. Agni means multiplied, in Sanskrit it means multiplied. Koti Phalagni multiplied by what? Bhukti, mean daily motion. Okay, it means daily motion. Gajya Bhakta, you see, the divided by the radius. Okay, divide. Bhakta means divided. Bhakta by radius. Kaladi Phalam, what does it do? This is the correction. Phalam means the result, which is the correction in minutes. Kala, you see, the units also are incorporated in this half verse. Okay, this is what he says. So he gives the correct this thing, So essentially, he is recognizing the fact that the derivative of sine is cosine. Now, Bhaskaracharya later, as you all know, it is 1150 CE, he calls it as Tatkalika Gati, okay, instantaneous velocity. See, all of us are used to the idea that instantaneous velocity, as if Newton was the first person to introduce it, okay. But he is saying even 5 centuries earlier, Bhaskaracharya is introducing what is Tatkalika Gati. He calls it Tatkalika Gati. He said the same thing. Koti Phalagni Mrudukendra Bhukti Trijyodruta Karki Mrugadi Kendre Tayo Yutona Grahamadya Bhuktai Tatkaliki Manda Parisputa Syat. Okay. What he is saying is the Koti Phala being multiplied by the daily motion of the Manda Kendra and divided by the radius, and the result added to or subtracted gives the instantaneous rate of motion of the Manda corrected planet. So here he is essentially using the Bhaskara takes delta sin m by delta t using the chain rule, delta sin m by delta m into delta m by delta t. Okay, we know that this is how we have to manipulate. Okay, and this is essentially implied. What he writes, this is what is implied. His this geometrical construction. So this is an arc. Okay, arc of a circle. You see it in blue. Okay. Now P1 corresponds to angle theta. Okay. So O is the center, and P2 corresponds to angle theta plus delta theta. Okay. So P1 O P2 is the difference theta, the delta theta. So theta plus delta theta. Theta, and then you add this small arc, then it's theta plus delta theta. Okay. Now the arc is r delta theta, and when the arc is small, we consider it as a straight line, and we consider it as a hypotenuse of a right angle triangle, small triangle, P2 P1S. Okay. So the arc can be replaced by a straight line. So then triangles P2S P1 and O T1 P1, they are similar, and P2S by P2 P1 is delta of r sin theta by delta theta is OT1 by OP1. So delta of sin theta by delta theta is cos theta. Okay. So this is how they arrived at this. This kind of geometrical. I will come to that later. In Yukti Bhasha, they will actually prescribe the geometrical construction, and they will go beyond this. I will come to that. In fact, that is the aim of the talk. Okay. So sine of theta plus delta theta is sine theta plus cos theta delta theta. You see. So this is a result, from even 950. Okay. And Bhaskara has even already given a this thing. Bhaskara has told her later. Okay. And he explains it, of course. He explains it more than Aryabhatta II and others. Okay. So this very much there. These calculus ideas were very much there, even in Bhaskara's Siddhanta Shiromani and even earlier works. Okay. So now, my aim of the talk is related to expression for the sine theta plus delta theta to higher order, to delta theta square. So this is stated in a work called Tantra Sangraha. Okay. So this is the work, the work of our text composed by Neelakanta Somayaji in 1500 CE. So myself and Ram Subramaniam have worked on that. So we have published a book, with detailed translation and detailed explanatory notes in modern notation. Okay. Of course, Tantra Sangraha does not give the derivations, and all the derivations are given in a book called Yukti Bhasha or the Ganita Yukti Bhasha, a work by Jeshta Deva. Okay, so that is about 30 years later, and this book is very important book and extremely well known nowadays. Okay, it is known for proofs and demonstrations. So Yukti Bhasha was, of course, translated by the great K.V. Sharma, and explanatory notes, both for the mathematics part and astronomy part, we have provided. We means Ram Subramaniam, MD Srinivas, and myself. Okay. And in this book, of course, it is more famous for infinite series for pi, sin theta, cos theta, and integration area. You see, especially infinite series for pi, sin theta, cos theta. These are well known nowadays quite a bit. At least people who care to know. But first, actually, it was the second order Taylor series was actually given by rather stated by Neelakanta Somayaji in his Tantra Sangraha. So how does he state it? Okay, how does he state it? We'll come to that. So in chapter 2, to deal with the two longitudes, there's a verse, two verses actually. The part of the second verse which we start, first verse is, he saying, Ishtado koti dhanushoho swasameepa samirite jedve savayave nyasya kuriya dunadikam dhanuho vigna aptaihi eka sharashaila shikindavaha nyasya chedaya chamita tatsamskara viditsaya chitvaika prakshipejyaha taddunushayoho अन्यस्यामत ताम विघ्नाम तया स्यामिति संस्कृतिः इति ते कृति संस्कारे स्वगुणौ धनुषोः तत्र अल्पीय कृतिं त्यक्त्वा पदं त्रिज्या कृतेः परः. Okay, so don't bother if you not follow the Sanskrit thing. What he says, having noted down the listed tabulated values samirita of the dorjyas or signs and kotijyas corresponding to the 2 points which are on either side of the arc, okay, whose dorjyas and kotijyas are desired, find a difference in the arc which may be in excess or short. Okay, so this, then the number 13751, okay, is in the Bhuta Sankhya notation. Professor Arvinda already talked about it. See, Eka Shara Shaila Shiki Indu. Eka means 1, Shara means 5, okay, Shaila means 7, Shiki means 3, Indu means 1. But you have to read it in the reverse order. So this is 13751, okay, and then divided by twice the mutual connection, etc., etc. Okay, he says this. Okay, this is the what he precisely states. Okay, so what is he talking about? Okay, so what is he talking about? He is talking about the following. Okay, so now this is the arc. Can you see the arc, please? Hello, hello. Can you see the arc?
Which one?
Yes,
Yeah,
yes.
we can see.
Yeah, yes, yes.
Yeah. So normally I written a quadrant. S. The arc stretching from S to P24. So that is a quadrant. Corresponds to 90 degrees of a circle. Okay. So now this arc is divided into 24 parts, okay? And so that is the normal way in which the arc is divided for convenience, in India, this thing. So each that sub angle, alpha, so the 24th part of 90 degrees, that is alpha, that is 3 degrees 45 minutes or 225, okay? And the radius of the circle is taken to be 21,600 by 2 pi, which is very close to 3438, okay? This is called trijya, okay, normally. So now the important thing is that suppose PI, you drop a perpendicular from PI to the OS, that is the horizontal line, okay? PI NI is the GR, okay? Corresponding to I alpha, okay? Angle I alpha, okay? And PN is the, if you add delta theta to it, okay, angle or arc or delta theta to it, okay, so then the GR corresponding to I alpha plus delta theta is NP. So now GR corresponding to I alpha is for I is equal to 1 to 24. So they are specified in text like Aryabhatiya, Surya Siddhanta, Siddhanta Shiromani, etc. In fact, please remember that in Aravinda's talk, he was saying about, you know, Kaki, Maki, Bhaki and all that, which is a verse in Aryabhatiya. Okay, so that is precisely the values of the signs, you know, R signs for, you know, the angle equal to 225 minutes, 450 minutes and all that. Okay, so invariably the 24 signs for these 24 angles are given. No, but how, what do you do with intermediate angles? So that is the problem which, you know, Nilakanta is addressing. Okay, so how to find out R sign of I alpha plus or minus R delta theta, that is intermediate value. Okay, that is between I alpha and I plus 1 alpha or I minus 1 alpha. Okay, so R delta theta. So the argument of the sign is here is in, you know, the arc, you know, that is, you know, it is given in minutes normally. Okay, so this is what is discussed in the quoted verses. Now he defines an intermediate quantity, you know, 13751. I told you that. He says that you divide this by twice the, you know, arc difference between the desired arc and the I alpha, you know, the stated, you know, tabulated value, you know. So that is R delta theta. You make, you know, you multiply by 2 and divide this D by this one. It is called Hara, you know, divisor. Okay. So now 13751, you can easily see that it is equal to 4R, okay, where R is, you know, 21,600 by 2 pi. So it in fact is extremely close to 13751. So we can take it as 13751 is 4R, so divided by 2R delta theta. So this D, the divisor will be, okay, 13751 divided by 2R delta, that is 2 by delta theta. So now this delta theta will be angle PPI in radians. Okay, of course they don't state it, but I'm saying, you know, this is how it is understood by Nilakanta Somyani. Okay, now R sin theta is Dorjia and R cos theta is Cotijia. Okay, so what he is saying is the Dorjia of I alpha plus or minus R delta theta is Dorjia of I alpha, which is known. Okay, plus or minus 2 by D into Cotijia of I alpha minus or plus Dorjia I alpha by D. Okay, so in modern language, okay, so in modern language it is R sin alpha, I alpha plus or minus R delta theta is R sin alpha plus or minus delta theta into R cos alpha minus delta theta squared by 2 into R sin I alpha. So this is precisely the second order Taylor series for an arbitrary angle, you know, which is close to one of the stated values I alpha. So similarly, you have got the second order Taylor series for the Coti. Okay, so these are the thing. So remember, this is all he is stating in 1150. Okay, sorry, 1500. Tantra Sangraha was composed in 1500. So now this is, you know, proved in Yukti Bhasha. Okay, so Tantra Sangraha is a Sangraha, you know, collection of Tantra and basically algorithms. Okay, so it only gives the rules, it gives the algorithms. Okay, it doesn't give the explanation, but Yukti Bhasha is gives all the explanations. In fact, Yukti Bhasha claims that it is a commentary on Tantra Sangraha, but it is true for the astronomy part, it is a commentary, but mathematics part is an almost independent, you know. He is talking far more than what Tantra Sangraha talks about. Okay, so it is a very self-contained work. Okay, so in particular, he is explaining the second order Taylor series. So what he does is, you know, you take a quadrant. Okay, OE and ON are perpendicular. You are considering the arc EN. Okay, so now arc the angle, you know, EOC corresponds to angle theta and EOC prime corresponds to theta plus delta theta. Okay, and arc CC prime correspond to delta theta prime and theta plus delta, so that is theta delta theta. Okay, then CB is sin theta. Okay, so right, because I am taking R is equal to 1 without loss of generality. So if angle COB is theta, then clearly CB is, if OC is 1, so CB is sin theta, okay? Sin theta, okay? And similarly, C prime B prime, okay, that is sin of theta prime, which is theta plus delta theta. And he takes the midpoint of this Shishta Chapa, he calls it, Shishta Chapa is what is left, after subtracting the multiple of, that fundamental unit of 225 minutes, okay? Shishta Chapa, he takes the midpoint of that. So the arc CM1, M1 is the midpoint. So arc CM1 is delta theta by 2. And now he takes M2 as the midpoint of this Chapa, CM1, okay? And triangles, now he says that the triangles OM1B1, okay, OM1B1 and C prime CD, okay, C prime CD, OM1B1 there is a big triangle, C prime CD is a small triangle, small rectangle. So they are similar right triangles, okay. So then one can see that, BB prime, then we get some relations, similarity relations. So similarly, triangles OM2B2, okay, OM2B2, okay. And M1CF, okay, there is another small triangle, so they are similar. He says that they are proportionality is there, that's what he says, okay. So then that also will give rise to some relations, okay. So I'll go to the next slide. So essentially he is saying that from the similarity of triangle BB prime, see BB prime is the difference between the sides, okay, that is CD. So that is equal to C prime C into M1 B1 and KK prime, okay. So remember that OK is cos theta, okay. Sorry, what am I saying? Sorry, CB is CB is sin theta and OB is cos theta, okay. OB is cos theta. So CK is also cos theta, okay. So like the C prime K prime is cos of theta plus delta theta, okay. So now finally he gets sin of EC prime, okay, that's what you have to find out. Sin of the an angle which is into the theta plus delta theta, so that is equal to C prime B prime, okay. The sin of this thing is angle theta plus delta theta, that is C prime B prime, okay. So that is equal to B prime D, he says, that is equal to CB plus C prime D, okay. So B prime D plus C prime D is clear. So now from the similarity of triangles, you are getting that C prime D is C prime C into OB1, and which is OB minus BB1. So he gets sin theta is equal to C prime C, sin theta plus C prime C into OB. C prime C is the arc, into OB. OB is the cos theta, cos of the thing, minus C prime C, there is again the arc, into M1C, okay, half the arc, into M2 beta, M2 B2. So now he says that M2 B2 is very close to sin theta anyway. Actually, M2 B2 sin of theta plus delta theta by 2, he takes it as sin of theta, okay. So finally he gets sin of theta plus delta theta is sin theta plus delta theta into cos theta minus delta theta whole squared by 2 into sin theta, okay. So Taylor series, please remember this is in 1530, okay. So this is the important thing, that in 1530, that they have got an explanation for this second order Taylor series, because they wanted for many purposes in astronomical calculations. So that is why he is giving this. And Nilakanta gives several approximations, more approximation for sin theta and all that. And of course, you know that for extremely good accuracy, you have the infinite series itself, okay. So, but this is okay for most practical purposes. This is good enough, you don't need much more accuracy, okay. Similarly, cos theta also he gives the Taylor series. So this is in 1530, okay. Now this is this result of Yantrasangraha and Yukti Bhasha, they are incorporated in later Kerala texts, like Sputanirnaya Tantra by one Achita Pisharadi. I'm working with that done with Rama Kalyani. So he is saying Bhujan, Lipti, Kutta, Sharirena, etc. etc. Okay, I don't have to this thing. So he also gives the same thing. Okay, so this will give you how they actually wrote those things. You see, sometimes it is said, oh, they didn't. I mean, how did we get right the equations? Because all the steps are given, and anybody who is familiar with the terminology will be able to construct the expression immediately. So again, they use the he gives some intermediate quality, hara, and all that kind of a thing, shishtakala and things like that. Finally, he also get the this is second order Taylor series, and for both cos and sine. And there is another text called Drukkarana, is highly Sanskritized, is in Malayalam, highly Sanskritized Malayalam text, and that also gives the second order Taylor series. So these I am working with pi, So Jau, in fact, this is written in Malayalam. See, imagine a scientific expression, you see, scientific explanation given in Malayalam, okay, 1600, you see. So remember, this is before any text was written in any modern European language, you see. Galileo was the first one to write in Italian and all that, So this gives, this Drukkarana gives a very big algorithmic text, and he is also saying it in Malayalam, but quite highly Sanskritized Malayalam. Javu Poyoru, just to give you a flavor. Javu Poyoru Sheshantan Povan Pora Tatagilum, Lipti Krutki Hares Vyasardam Kondata, like that, etc. etc. Okay? So he is giving the same expression. So very clear. You see, there is no ambiguity about all these things, He is given the expression, but in words, okay? So that is the important thing. So I got a little more things today, but there is no time. I think I will. They also give another in the Sputanirnaya Tantra. They also talk about derivative of a ratio of two functions. See, that is very important. The ratio of two functions. So that is given in this text called Sputanirnaya Tantra and many other texts. Okay, I think I will stop here. Okay, so now I think I request Pai Venkateshwar Pai to take over after 1 minute. Okay, please. So now we'll have the talk by Venkateshwar Pai. Yeah.
Hello. Can you see the slide now?
Yes, we can see. Yeah.
Hello. Okay. Yeah. So the talk that I'm going to give is continued technique economy.
Really, Pai,
Hello.
Unmute and talk. Yeah.
Yeah, it's unmute actually.
Pai, please unmute and talk, Pai.
Yeah, it's unmuted actually. It's unmuted.
Now it is heard. Okay, go.
It's not audible.
Who has introduced?
Pai, it is not audible.
Hello.
Pai, please talk.
Hello. I'm talking.
Go ahead.
Hello.
Go ahead. Not audible, Pi. Why don't you? I don't know. You are not audible.
So now
Not
can you?
audible.
Now it is audible.
Now it is okay. Yeah, yeah. You talk.
Yeah. So okay. I'm using simultaneously both the phone and the okay.
Okay.
Yeah. So the Karna Paddhati.
Pi.
Hello.
What I suggest is, you go out of the system and come again, that may be better. We are not hearing you at all.
Okay.
Better you use laptop mic instead of. Are you using headphone?
Yeah, I'm using headphone
No,
through
better
mobile and the
laptop. It will be better, I think.
laptop. I think you were not able to hear, right? So I'm using slides through laptop. Let me.
Yeah, you do it again, yeah.
Yeah. So now. Can you hear me now?
So incidentally, can you hear me?
Hello.
Why you do it without slides first and then share screen and let's see. You start talking.
Sriram, can you hear me?
Yes, I can hear you. I can hear you.
Okay, can you quickly tell me what was the question asked to me?
No, that is Sophie, Sophie was asking, Mama. Professor Sophie, yeah. We'll come to that.
He is still there?
Sophie, are you there? Can anybody I forgot, Professor Sophie? Professor Sophie. Professor Sophie doesn't seem to be there. Is Partho Mukhopadhyay there? Partho?
Hello.
Partho? We'll come back to it, Amartya. We'll
Hello.
come back.
Can you hear me?
Pi, can you know?
Yeah, I can. Yeah.
You talk for 1 minute, You talk without sharing, then we'll see.
Host has been sharing.
Huh?
Somebody has disabled. So I'm not able to share the screen. Host disabled. It says host disabled.
Raja Das, are you there?
Yes, sir. Already I made him co-host again because he left. He joined once again.
No, Professor Venkateshwar Pai.
Already
Yeah.
he can share, sir.
Okay, yeah, he can share. Yeah.
Okay.
Pai, you try. Yeah, he started, it says, yeah.
Hello, can you hear me?
Yeah, we can hear.
Yeah, okay.
You share the screen.
Yeah. So, Karna Paddhati is a unique treatise which gives the rationale for astronomical algorithm and parameters.
No, we can't see we can't see the screen, Pi. We can see only that your folder we can see. We can't see the screen.
Okay, maybe I can see that. Maybe I will wait for some time.
I also have the same problem. PDF we are not seeing.
Yeah.
No, we can't see.
Sir, again, you stop sharing and once again you do it. Share the screen. If you do the share the screen, whatever you are seeing on the monitor, you will be getting that one.
Share the screen, Pi, now. Yeah.
Yeah.
Okay, now you do it. Oh, yes, we can see. We can see the screen. Yes.
Yeah. Okay. Yeah. Here also, right?
Yeah, we can hear. So just go fast. Yeah.
Yeah. Okay. So, so I'm just skipping the previous slide. Yeah. So.
See, there's a problem, Still.
All composing the context. Hello.
Yeah. Now go ahead. Let's see.
Yeah.
Go. Yeah.
So it is in this context, the author of Karana Paddhati makes use of Valupasamhara extensively to provide rationale for different economical problems. So in Karana Paddhati, a very sophisticated understanding of the mathematical properties of the continued fraction expansion of a ratio of two integers g and h.
Yeah.
And the ratio
We can't hear.
Hello. So he says you give Mahara. So let G and H denote the two large numbers corresponding to Mahagunakara and Mahahara. Gunakara and Mahahara are used for multiplier respectively. Mahahara.
It's not clear. Shall I suggest something?
Yeah, sure.
I will talk, I will talk, you put the slide, okay?
Okay.
That may be better. You mute it, I will say, yeah.
Yeah, sure.
Because, can everybody hear me?
Yes, sir.
Okay. So now let G and H denote two large numbers corresponding to what are known as Mahagunakara and Mahahara, okay? So now we have to get the ratio, okay? Now assuming H by G, we divide H by G, okay? So let the quotient be Q1 and R1 be the remainder. So H by G is Q1 plus R1 by G. Okay, next step. You see, now divide G by R1, you see remainder, okay? G by R1, which is Q2 plus R2 by R1, okay? And then again divide R1 by R2, so you get Q3 plus R3 by R2. So like that. So in general, Rn minus 1 by Rn is Qn plus 1 plus Rn plus 1 by Rn. See, please, this is that more or less the Euclidean algorithm. See, don't. So H by G in this way can be written as Q1 plus 1 divided by Q2 plus etc. So it's written as a continued fraction. Okay, H by G is a continued fraction. Okay, next slide, pi. Next slide. Pi, next slide. Okay. So this is written, in a sequence, called Valli. Okay, Q1 to etc. Qn minus 1, then Qn plus 1, and then finally you put 1. Okay. So in the next step, what you do is, this Qn plus 1 is there, no? So what you do is, you multiply by the one above, the Qn, okay, and then add one below. So in the next step, so what was there that corresponding to Q1 is Q1 into Qn plus 1, okay, and other things remain the same, okay. So next slide, pi. Next slide, okay. So like this, you keep doing, in the next this thing, yeah. So you can get a sequence of these things, So that is essentially, see, for the second, how I got it, I told you. The third column, so the second column, you see, whatever be the non-trivial entry, you multiply it by Qn minus 1, okay, multiply by that, then add what is there below. So it is like that, Qn minus 1 into this thing and all, Okay, you continue, you go to the next. So finally you get two numbers H1, Gn, okay. So he is giving an example, for instance, for the rate of motion of the sun, okay, G is 576 and H is 210389, which is the Gunakara and Haraka of the sun, okay. So H by G is 210389 by 576, it is 365 plus 149 by 576, okay. So then again we multiply, quotient is 365, remainder is 149. So we again divide 576 by 149 to get 3 and so on. Okay, repeating these things. We get the Vallis, quotients as 365, 3, 1, 6 and 2. Okay. So we terminated the process of mutual division with Qn plus 1 is equal to Q is equal to 5. So this is how we are terminated. Okay, next slide, pi. Next slide, pi. Next slide. Okay, this is how you get. Okay. So next slide. Okay. So repeating the thing, still only two terms remain. Okay. So because you are cutting off one entry, last row, you see. So finally you get two entries, 21185 and 58. Okay. So this is precisely the method used for the linear indeterminate equation, Kutaka. Okay. Here it is done for getting the these things, various approximations for the ratio. So 58 and 21185, there's alpha, because you have stopped at some stage, and there's the alpha gunakara and alpha hara. Alpha is small, okay? So that's why 58 by 21185 is an approximation to 576 by 210389, which is correct to more than 4 decimal places. Okay, next slide, pi. Next slide, pi. Okay. Okay. So now this is written in this kind of columns. Okay. So like this. Okay. And next slide. Okay. So you get successive columns and all that. That's what is precisely given. Okay. So is finally that's how the successive divisors are given by this kind of a thing. It is in the you get H1 is Q1, H2 is Q1 into Q2 plus 1, H3 is Q1 into Q2 plus 1 into Q3, etc. That's how you can generate the nth term. Okay. Next slide, pi. Yeah. So similarly, generate the alpha gunakara also, So, but so no, yeah, okay. So gunakaras also the these things also the multipliers also you do like this is essentially same thing. Okay. So yeah, next slide, yeah, next slide, yeah. So this is the please no previous pi. Yeah, okay. So now essentially you see the previous the table of numbers. Next one, pi, next one. Yeah. Please stop. So you are getting, see, because we have all worked on Karna Paddhati, that's what I'm saying. Because these all worked out by pi only. Now I'm saying, you see, the thing is last two rows, no, they are you have to take the ratio of them. You have to find that out, you see. So now the small divisors and small multipliers, you see, that's what we are getting, 27 into 1. You see, these humongous numbers in the at the bottom, the ratio of that is in the first approximation is 27 by 1, next 28 by 1, the better is 55 by 2, the better is 248 by 9, then 3031 by 110 and so on. Okay. Next. So that is how you generate the, yeah. So this is how you calculate the moon's so-called anomaly. Okay. So for finding the moon's anomaly in order to apply this method, to generate longitudes for moon, he is giving a figure, he is giving when the moon and its apogee are, coinciding at sunrise. Okay. So in the 1 minute, the khanda is a day, you see, from the epoch, it's a day on which they are equal. The apogee and moon are in the same direction. Moon's apogee and actual moon are in the same direction. Okay, next slide. Next slide, yeah. Yeah. So for khanda for a given epoch is a very beautiful formula that Pudumana Somayaji has given. Okay. So you have got a successive, divisors and multipliers. Okay. So for any day, okay, or any ahargana, okay, this is how you can find out this khanda. You find out the so-called reminders, and the khanda dida will be for any remainder. See, so you for any day you have to find a day close to it on which at the sunrise the anomaly must be 0. Okay, and that is what you have done by this using these successive multipliers and divisors, and is using a Kuttaka equation. Yeah. Next slide. Khanda dina. Yeah. Next slide. Yeah. So this is the rationale is given. I think there's no time for that pi to get going. So it is all solving linear indeterminate equation, Kuttaka equation. Okay. So and there are some very simple properties and all that they are all done. Okay. So next slide. Yeah. General solution can be given. Okay. Next slide. Yeah. Now see in this previous. Yeah. See, sorry, I mean, see this in the Pudumana Somayaji's method, you see all the quotients and all that, remainder, the whole thing involves only positive numbers. But you can do better, you can do semi-regular continued fraction. So what Pudumana Somayaji corresponds to do in what has done is regular continued fractions. Now you can use semi-regular continued fraction. and that is what is discussed in Drukkarana. You see that is, please listen carefully. This is an important thing. Bhaskara, this Chakravala method for quadratic indeterminate equation is equivalent to doing semi-regular continued fractions for root of d. You see, so similar technique is used here, but for a simpler problem. Anyonya haranam chayu bodhinam. So this is what is given in Drukkarana. Okay, next this thing, yeah. So he is given the whole procedure. Yeah. So here, this epsilons. So what he is saying is the remainder, at any stage, if it is less than the previous remainder by 2, then you retain that. But if it is, you take epsilon is equal to 1. If the remainder is greater than the previous remainder by 2, then quotient is replaced by quotient plus 1, and remainder is replaced by Ri minus 1 minus Ri. Okay. So like that, you have a procedure, okay, with both negative and this thing coming, so that you have a semi-regular continued fraction optimally. Yeah. Proceed. Yeah. Yeah. So okay. So this is the first set of this number that is given that is in the Pudumana Somyaji's thing. You see, so that is using regular continued fraction. Whereas in the next table, you see, next sub table 2, that gives as both the positive and negative kind. That is the semi-regular continued fraction expansion. Okay, this is the 2. So that is what is done by Drukkarana, and he gives the properties also. Okay, next this thing. You try talking, let us see. Try talking, Pi, let us see. Try talking. So this is the work, It is all these details are given in this book.
Yeah. So this is finally.
Yeah, tell me. Yeah, tell.
This is finally all technical things you have already told. Now I acknowledge the collaborators.
Yeah. Okay, very good. Yeah.
I acknowledge the collaborators, Ram Subramanian and Mr. Professor Sriram and Srinivas.
Maybe you can, if you want to say anything, you say, without sharing, because doing both is giving problems for you. You see, so stop sharing and they talk. Let us see.
Yeah. Hello. 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 Hello.
I stop sharing and talk for a few minutes.
Yeah. Hello.
Talk.
So this is essentially to emphasize the Valuation methods, both the methods given in Karana Paddhati, and how Puduma Somayagi extensively used these two techniques and properties of these techniques to solve different astronomical problems in Karana Paddhati. And also, a century later, Drukkarana, the author of the Drukkarana is not known. Drukkarana is composed during 1606, and it is composed in a language called Manipravalam, which is a mixture of Sanskrit and Malayalam. So we can say that it's a hybrid of Indo-European and Indian languages. Yeah. So where you can find the semi-regular continued fraction technique.
Actually, it is just 5:36 now. Anybody wants to make any comments, please do so. Datta, Arvinda, or any of the participants also, you can make comments.
Yes, I'm there. Just wanted to say that. Yeah.
Yeah.
Sriram, can I ask you a question?
Yeah.
No. So, yeah, you translated this Yukti Bhasha and you also looked at some of the later Sanskrit texts and so on. My question is, the mathematics content in the Sanskrit verses, does it become easier over time or is it still as terse as earlier ones? I'm just asking.
No, yeah. See, in fact, I found it, I am not I can never translate by myself, okay? In fact, Yukti Bhasha was actually translated by K.V. Sharma, okay?
Okay.
Of course, Tantra Sangraha was done by Ram Subramaniam completely. And Karana Paddhati was mostly by, Pai only, Venkateshwar Pai only translated, okay? Okay, but now I can see that I can understand more, So in fact, when in his work called Siddhanta Shiromani, myself and Pai are sitting together and translating, you see. So Pai translates, and now I can make even corrections, because I can know enough Sanskrit, now, you see, the technical Sanskrit, you see.
Okay.
So there are some very standard expressions, take the sign, take this thing, multiply, divide, and one gets used to it, and one can make out the Sanskrit fairly easily. Yeah.
Okay. Yeah. And the brevity still is there. I mean, brevity of expression.
Oh yes, definitely. Oh, definitely.
The Brikarna is an example for that. Brikarna, Brikarna, very quick and very cryptic. So we used very cryptic, right? Hello.
Yeah. We can hear.
Yeah, Brikarna is very cryptic. Yeah. As we are working on. Yeah.
I see.
Yeah. See, Aravinda, what happens is, hello?
Yeah, I'm hearing, yeah.
Yeah, see, some of the Western scholars, you see, they don't know Sanskrit that well. See, but they tried hard, So sometimes they translate, the verses and all that just using dictionary. See, like Professor Bhaskaracharya,
Yeah.
So they had done it, But so what the problem with that, approach is that they will be too literal, you see. See, that may be for pros some problems, you see. See, for instance, some article I wrote, okay? With the translation, with help in translation by, Ram Subramaniam or Pai or Sita Sundar Ram and all that, okay? But when it went to so we take some liberty, we know that is allowed.
Right.
But it went to Hayashi. You see, Hayashi will be very careful, he will insist on completely literal translation.
Oh, I see.
Yeah. So they do things, so they have to struggle hard, and they do, you see.
Okay.
But that is why for translating the whole book, see, now Pingree has not done it. You see, maybe one small work,
Correct.
Kim has not translated a work.
Yeah.
I see, but of course he's an expert. Nobody denies it. You see, that is because, it is difficult. Taking some verses and all that, in which you are all already familiar with the content, then you can do. But the whole book, you see, little more Sanskrit, Malayalam or whatever.
No, definitely.
Yeah, that's what happens. Yeah.
Yeah. No, I understand that. Yeah, that's what I was asking. That's why I was asking because
Yeah.
you need to know so much of culture, this thing, and so on. It's sort of
Yeah. And also immediately, see that in one of the translate, this is we have to translate. Can you hear? Yeah.
Yeah, I can hear.
Yeah. So we were saying, Jalavega was comes, this thing. Jalavega, in Katapayadi notation, it will become 3438, which is a Trijya, you see. So familiarity is important,
Correct.
So as soon as Jalavega comes, we'll, in the sleep, we will put 3438.
That's right.
Because it is hard, and it will also tell you what he is trying to do, So that way the familiarity is important. Yeah, one learns over.
Correct. Familiarity is definitely very important.
Yeah.
I mean, that was my point actually. Yeah. Because things are
Arvind and Sriram, I come back.
Yeah, please. Yeah, make some comments. Yeah.
No, I think Amartya wanted to know.
So Sophie's thing, I don't know, but anything else you can say, Amartya.
So the question to some is that what is the date of Karna Paddhati that you have fixed? I mean, there has been some confusion about the dates.
1536, from various these things, in fact, Pai will be able to say more this thing, definitively about that. So using various things, it was dated later, but by all indications, by the kind of things he knows and by the kind of familiarity he doesn't have with some of Nilakanta's concepts and all that, we have put it around 1550, Karna Paddhati.
So same as Nilakanta.
No, Nilakanta was 1500. Tantra Sangra was 1500. Jeshtadeva, we say it is around 1530. So it's slightly later.
Maybe I can say something on the date.
Yeah.
Nothing. There is a Khandadina for the lunar calculation.
Yeah.
And two Khandadinas differ by some 12,000 or about 25, 28 years. So if it were later, so within about 30 years, you can date a Vakya text by the Khandadina they take for the calculation of the position of the moon. So that's how Vakya Karna was dated at around 1280 or 1290. So in the same way, Karna Paddhati by the sort of the 30-year gap between the Khandadina it takes. And then there is another verse of Puttumana Somyaji, something called Venma Rohashtaka, where he is giving a Khandadina. So using that also you can date, and so his Puttumana Somyaji's period comes around middle of the 16th century. He is a junior contemporary of both Jeshtadeva and Nilakanta.
Yeah.
The 18th century date is because in Charles Wist's paper, he seems to say that somebody in 1820 told him that Puttumana Somyaji was about 100 years earlier. But that is not borne out by any other evidence.
Okay, good.
1532 is the
MD, do you want to make any other comment?
So this semi-regular continued tractions occur for the first time in Dhrikarana is perhaps what we see in the rational approximation of a rational number. But it is occurring in Bhaskara's thing, not as a continued fraction, but similarly in the division, mutual division, they are allowing for positive and negative signs. And that's how it occurs in Chakravala. When you reinterpret Chakravala as a continued fraction expansion, it becomes a semi-regular. So in Bhaskara, semi-regular continued fraction doesn't occur directly. But in Dhrikarana, it is explicit.
Correct.
It is explicit. You are taking a ratio of two very large numbers, and these various convergents are giving different rational approximations to that. And they are using the semi-regular expansion to get at good rational approximation in smaller number of steps. So all that is recognized in Dhrikarana. That was the main thing.
Yeah.
So just to get to my idea is clear. So the question is to Srinivas.
Yeah.
That during the initial discussions about Bhaskaracharya's Chakrawala, so Iyengar and then Selenius, they had talked about this semi-regular thing about these negative coefficients, etc. So is it that what they're talking is same as I mean Iyengar and particularly Selenius? Is it same as Karna Paddhati, or there is some difference in the way it is being talked about? I mean the 20th century interpretation in terms of semi-regular and Karna Paddhati, is there any difference?
No difference. In case of the Varga Prakriti or quadratic indeterminate equation, in fact, even in Europe, a semi-regular continued fraction was discussed by Minnegerode for the first time in the context of solving the so-called Pell's equation only. And that was in 1870s or 1880s. That was what is called the nearest integer continued fraction expansion, which is a semi-regular continued fraction. And what Krishnaswamy Iyengar showed was that Chakrawala, the actual steps, is a different semi-regular continued fraction. It is not nearest integer. It is what he called Bhaskara continued fraction, which later on Selenius repeated the same thing. Selenius has not added anything to the continued fraction part of it. He tried to generalize this kind of a continued fraction to an arbitrary real number from what Krishnaswamy Iyengar had done. But later this Australian group, Matthews and others, they have called it nearest square continued fraction. And I mean, one can call it whatever. It's not nearest. But the Karna Paddhati thing is not dealing with a irrational number. It is only dealing with a simple ratio of two integers, but a ratio of two very large numbers. So it's a straightforward, what you can call Euclidean algorithm or calculation of GCF or whatever, mutual division of one by the other and the remainder dividing the next. And in this, you can do the nearest integer instead of keeping all the, you don't, if the remainder is less than half the divisor, half the divider, you keep that remainder. If the remainder is more than half the divider, you take the larger quotient. So that continued fraction expansion will be a nearest integer continued fraction expansion for a rational number. So this semi-regular expansion that Karna is talking is actually a nearest integer continued fraction expansion for a ratio of two large integers for a rational number.
Okay, so there is a difference between this. So that is Chakrawala is for irrational, and this is just the basic thing. It's more about the Kutaka.
Yeah, this is just the basic thing. As he said, Euclidean algorithm kind of thing. Only thing is, Dhruv Karna, you deal with negative these things also, nearest integer as MDS said. Yeah, so that is the thing. Yeah. Yeah, any other comments? Then if there are none, I will close the session. I mean, academic part.
No, I just I rushed through some of the slides. Is there any confusion about? I can just say a few things. I don't have to open the screen, but like towards the end.
No, I think it was quite clear. All these, that item potential, all those things were, I think, quite this thing. It was quite all right, and how, you have to interpret properly. It was clear, I think. If somebody has some specific things, they can ask. Yeah. Okay, then we will thank all the speakers, thank all the participants, and people.
Thank the organizers for organizing a very interesting session.
Very interesting.
Yeah, thank you very much for everything.
Yeah, thank you.
Okay, thank you, and thank the overall organizers of the conference for allowing this session. I thank the
I sincerely thank you, the chairperson, Professor M.S. Sriram sir, for conducting this session very lively and a wonderful manner. And I thank all the invited speakers for their excellent speech. And I sincerely thank all the participants for your feedback. Thank you all. Thank you so much.
Yeah, thank you. I also want to thank Professor Piyush Chandra. He was the person who, contacted me for, convening one session, convening this session. So I thank him also. Okay, thank you.
Thank you. Thank you so much. Thank you so much.
Okay, yeah.
Thank you.
Okay, the session is closed now, yeah.
Okay. Thank you.